Hi students, this is Mr. Yao. Today we are going to talk about the next lesson in matrix, which is matrix multiplication. First, some prior knowledge. Are these matrix operations possible? Why or why not? This is something we have learned before in the previous lesson, and the one word I've emphasized on in the previous lesson was dimensions. That means every single time you want to work with matrix, you've got to check their dimensions to see if you can work with them or not. So A, the dimension for the first matrix, that's 2 rows, 3 columns, so it's a 2 by 3. For the second one, it's a 2 by 3 as well. That means we can actually work with them. So 0 minus 10, negative 10, negative 2 minus a negative 2, be careful with that. That's negative 2 plus 2, which is a 0. 4 minus 30, negative 26. 1 minus 42, negative 41. 1 minus 5, negative 4. And 5 minus 61, negative 56. That is A. For B, first matrix is 2 row by 3 column, 2 by 3. Second matrix is 2 by 2. They're not the same dimensions, so no, we cannot work with them. Reason, not the same dimensions. So that is B. Now let's get into today's lesson. In the last lesson, we have learned that in matrix operations, well actually before we get into this lesson, I do want to actually let you know matrix multiplication is a procedure that you have never seen before or learned before. And you haven't done anything alike. So please make sure you're doing that practice to get the procedure down. There may be several different ways to do it, but I am choosing one specific way because to me, I do think it is quite consistent that you are doing the same thing all through the matrix for each step. So now let's actually have a look at the matrix multiplication. We have learned that in matrix operations, dimensions are the most important, and that goes for matrix multiplication as well. Matrix can only be multiplied under certain circumstances. Now let's have a look at these circumstances. 3 lines of words. The number of columns in the first matrix must be the same as the number of rows in the second matrix. That sounds, kind of complicated, and especially adding the next sentence. The resultant, which means the answer matrix, has the same number of rows as the first matrix and the same number of columns as the second matrix. Well, you might be wondering, wait, that's like first row, second row, like a column, first matrix, second matrix, column, row. What if I mix them up? Yes, quite possible. That is why these words has a simpler way to interpret. So now let's have a look at some examples and interpret these words. Now, A. So that just means when we have the subscript as in that form, that just means it's some kind of matrix that follow that kind of setup. So A, then 3, a multiplication sign 4, that actually means it's a matrix that is a 3 by 4 matrix. So these represent the dimensions. Starting from now, we're not going to write the word by anymore for dimensions. We are going to use a multiplication sign. When I say multiplication sign, it's not the dot, it's the cross. So for the first one, that means I have 3 rows and 4 columns. So in the previous slide, it did say the number of columns in the first matrix and the rows in the second matrix. Here, the number of columns is right here, 4 for the first matrix. Number of rows for the second matrix is right here, 4. And they are the same, so yes, we can actually multiply them. And now if you look at these, when we write down the numbers, we basically are deciding using the inner dimensions. If the inner numbers are the same, that means we can multiply them. Now let's go back to the previous slide again. The next thing it says is the resultant has the same number of rows as the first one and same number of columns as the second one. Rows of the first one is right here. Rows of the first one and columns of the second one is right here. That's going to be our new dimensions. So that's our new dimension, row dimension, and that's our column dimension. That means our new matrix is going to be a 3 by 2 matrix. And that, as you may notice, we are using the outer numbers. So the inner numbers decides if you can multiply the matrix or not, and if you can, the outer numbers will tell you the new dimension. So now let's look at B. Same idea. Look at the inner numbers, 3. They are the same, so yes, we can actually multiply them. Now you look at the outer dimension, outer numbers, that's going to tell you the resultant is going to be a 4 by 2 matrix. Next, C. Inner numbers 2 and 4. Clearly they're not the same, so no, we cannot multiply these two matrices. That is example 1. Kind of just giving you a general idea about how to decide if you can multiply or not and get a general idea of what you may get. Moving on. Multiply matrices. We multiply the elements of the corresponding row and column and then add them together. So as of right now, you may not fully understand what the word corresponding here mean. We will see what it means in an example later. But mainly these words are just telling you when we multiply matrices, we're not only multiplying, we're going to multiply pairs and then we are going to add all the pairs together. Just like a number operation, the dot is optional. That is just saying, for example, let's say we have 2x. We can write it as 2 times x or 2x. It's referring to that little dot. So if you have matrix, you can choose to write the dot in the middle, or you can choose to not have the dot. They both would represent multiplication. Now it's time for the steps. Example with steps. First step, check the inner dimensions first to see if you can actually multiply the matrices. That's what we just talked about in example 1. So let's check the dimensions. 2 by 2, and another 2 by 2. Inner dimension, same. That means yes, we can multiply. And the outer dimension, 2 by 2 is going to be our result. That's why the next part of step 1 is if you can, determine the dimensions of the resultant. Step 2, draw the brackets and a blank space for each of the missing elements in the resultant. And please make this into some pretty big matrices. You will see why. So now I just know I have a matrix that is a 2 by 2. And we are drawing lines, blank space, to represent each of the missing element. 2 rows and 2 columns. Okay, that is step 2. So far, we are kind of just checking and setting things up. Now it's time to get to the real stuff. Step 3. In each blank space, write down numbers in corresponding row of the first matrix. First matrix, we're going to look at the row. So 1, 2, that is the row. We're going to write these 2 numbers inside each space of the first row. And we are spacing them out because we're going to need space for columns later. And now the second row right here. So I'm going to write them in the second row in each space. 3, 4, 3, 4. That is step 3. Moving on, step 4. In each blank space, write down numbers in corresponding column of the second matrix next to the numbers in the previous step. So now we're looking at, because we already wrote down all the rows from the first matrix, we're not going to get columns from the first matrix as well. We're going to do it with the second matrix. Column 5, 7. So I'm going to write them into each space of the first column. 5, 7, 5, 7. You might be wondering, wait, but like it looks like you are writing these numbers in a row. Well, not quite. Let's be very clear. These are spaces. These are the 4 spaces. There's no rows or columns inside these spaces because in the next step, I'm going to do operations with these numbers inside each space. So I am merely trying to get all the numbers from rows and columns into the spaces. So I am actually writing them in column because I got in this 5, 7 here, and then I move on to the bottom, which is another 5, 7. They're all in the first column. Moving on. Now we are doing the second column. Numbers are 6, 8. So I'm going to put them in the space 6, 8, and 6, 8. Lastly, in each blank space, multiply numbers in steps 3 and 4, then add them together. So next, we are going to look at the pairs of numbers. Multiply numbers from step 3 and 4. Step 3, I used color red. Step 4, I used color purple. So I am going to multiply the step 3 and step 4 numbers, then add them together. Multiply the step 3 and step 4 numbers, add them together. Multiply, add, multiply, add. Now I just need to calculate out every single space. 1 times 5 plus 14, that is 19 in the first space. 6 plus 16, that is 22 in the second space. 15 plus 28, that is 43 in the third space. and 18 plus 32, that is 50 in the last space. Now, something else to help you. The inner numbers that we got are 2's. And inside each space, we have 1 pair, 2 pairs, 1 pair, 2 pairs, 1 pair, 2 pairs, 1 pair, we have 2 pairs of numbers. So that inner number will always tell you how many pairs of numbers you will get. And we are multiplying the pairs and then add all the pairs together. So that is example with steps. Now moving on, example 2. Let's try that again. The process. First, check the dimensions. First one is a 2 by 2. Second one is a 2 by 1. Clearly, inner numbers are the same. So yes, we can perform the multiplication. And our result is going to be a 2 by 1. Also remember, these numbers tell you that you will actually get 2 pairs of number in each space. The 2 by 1 matrix, so let's draw it out. A 2 rows by 1 column. Now we're going to look at the first row, that's 1, 4. Second row, -3, 0. And then we have 1, 2 in the first column. So 1, 2 in the first, 1, -2 in the first column. We only have this one column, so we're going to just write these numbers in there. Next, multiply the pairs, add in the middle. Multiply the pairs, add in the middle. And that will give us an answer of -7, -3. That is example 2. Now you can pause here. If you feel like you're kind of getting the process, you can try example 3 by yourself, then come back to check the answers. But here's number 3. Dimensions first. That's a 2 by 2. That's a 2 by 3. So clearly, my inner numbers are 2's. They're the same, so yes, we can multiply, and we will have 2 pairs of numbers in each space. Our resultant is going to be a 2 by 3 matrix. So let's draw it big. 1, 2, 3. 1, 2, and 3. Now you may see why I'm asking you to draw them big, because we're going to put quite a few numbers on there for each space. And the space is merely for you to keep track of the numbers so that you understand, you know by yourself which numbers actually belong to the same space, so you will not mix yourself up when we're trying to calculate them out. So let's have a look. First row, 2, 4. 2, 4, 2, 4, 2, 4. Second row, 1, 1. 1, 1, 1, 1, 1, 1. Next, let's deal with the column. First column, 1, 0. First column, 1, 0, 1, 0. And now you may kind of notice why we are checking the dimensions. Because if, for example, in the second matrix, you have 3 rows by 2, these numbers are different, then you can actually match them up. You don't have 3 numbers in the first matrix to match up with the 3 numbers. So that's why we got to make sure the inner dimensions are the same. Second column, -1, 2. So -1, 2, -1, 2. Third column, 0, 5, 0, 5. Now it's time to multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add. And oh, I forgot to make my marks to show you clear. That's second column and that is third column. So I'm just matching them up. That's second column, the other one is third column. Okay, now lastly, we just need to calculate all the numbers out. That's going to give you 2 in the first space, 6 in the second space, 20 in the third. Next, 1, 1, and 5. So that is my final answer for example 3. Moving on. So now it's time for you to kind of try. You can pause here and try example 4, 6, and 7. Example 5 is slightly tricky, so I'm going to show you how to do 5. But you can pause here and check back later for some answers. Now example 4. That is a 2 by 1 matrix. That is a 2 by 2 matrix. The inner numbers, not the same. So, N, A. We cannot actually multiply them. And example 5. I'm actually going to go to example 6 and 7 first, then come back to example 5. Example 6. 2 by 2. 2 by 2. I'm going to start going a bit faster. In the numbers are same, so yes, and resultant is going to be a 2 by 2. So here is my matrix, 2 spaces, 2 spaces. First row, 4, -1, 4, -1. Second row, 1, 5, 1, 5. And then time for column. First column, 1, 9, 1, 9. Second column, 3, -6, 3, -6. Lastly, just need to multiply and add, multiply and add, multiply and add, multiply and add. So final answer, we're going to get -5, 18, 46, and -27. That is example 6. Next, example 7. That is a 2 by 3 matrix. That's a 3 by 3 matrix. Inner numbers are 3, so you'll have 3 pairs of numbers inside each space. Let's be clear about that. This, again, the middle number, the inner numbers will tell you you will have 3 pairs of numbers. Resultant is going to be a 2 by 3 matrix. Let's make it big. 1, 2, and 3. 1, 2, and 3. Trying to make them big, so we have all 3 pairs of numbers in there. First row, 3, -1, 1. 3, -1, 1. 3, -1, 1. 3, -1, 1. Second row, 0, -2, 5. 0, -2, 5. 0, -2, 5. And as you may notice, doesn't matter what kind of dimensions we get, we are following the exact same procedure. Deal with the rows first, and then set the columns up. Afterwards, just multiply and add. Doesn't matter what dimensions you may get. This is a universal method. Here, first column is 1, 0, 0. So 1, 0, 0. 1, 0, 0. Second column is 0, 1, 0. So 0, 1, 0. 0, 1, 0. Last column, 0, 0, 1. 0, 0, 1. Now I can just multiply the pairs of numbers and add in between. Multiply a pair, multiply a pair, multiply a pair, adding in between. Multiply a pair, multiply a pair, multiply a pair, adding in between. Same thing for all of them. Multiply, 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 add in between. Multiply, 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 add in between. Final answer, you may get 3, -1, 1, 0, -2, and 5. That is example 7. Now let's go back to example 5. Example 5 is slightly different just because the rows, you don't have many numbers. So first matrix is a 2 by 1, second matrix is a 1 by 2, and the middle numbers in the numbers are 1. So yes, you can multiply, and you are going to have 1 pair of numbers inside each space. Resultant is going to be a 2 by 2. So that's why it kind of looks slightly different, because you are kind of making this matrix bigger in the final answer. So let's set it up. 4 spaces because it's 2 by 2. And then we are still going to look at rows and columns. First row is just a 3. Well, then you're just going to put a 3 inside the first row. Second row is a 2, so you're just going to put 2s inside the second row. And then first column, -3. Second column, a 4. The difference is, for this one, you only have 1 pair of numbers. So you are just not going to add anything together. We are simply going to multiply all the pairs. And that's going to give you -9, 12, -6, and an 8. That is example 5. Now moving on. Oops, went to a different place. Here it is. For some matrix multiplications, we could have formulas. So I did say there are formulas, so I'm going to show you the formulas and kind of for you to see how crazy it may get. 2 by 2 times a 2 by 2. Here's the formula. And 2 by 3 times 3 by 2. Here's the formula. They look quite crazy. So you probably do not want to try to memorize the formulas. But it kind of works the same way. You see, first row, A, B. So A, B, A, B. Second row, C, D. C, D, C, D. First column. Let's see, first column, we have E, G, and EG. So E, G, E, G. Second column, FH, FH, FH. So still work with the procedure. Doesn't matter. So you see, for these, it's pretty hard to remember. It's also not universal because you have a formula for every single different setup. So it's better to understand the process that we just went over, which would actually work for any dimension. It's a universal method. Moving on. Let's look at example 7 again. When you are working on it, you probably have noticed something about example 7. If we look at example 7 again, right here, that's our first matrix, and that is our answer. Now that I have highlighted them, you may have noticed they are exactly the same. So there must be something special about the second matrix to make that happen. So now let's talk about that. In example 7, you may have noticed something about the answer and the original question. It is almost like we multiply the matrix by 1. And that is something we have learned in the first unit called multiplicative identity. That means when you multiply a 1 with a number, you are just going to get that exact number back. And this is what's happening with the matrix. That means the second matrix is special and is called an identity matrix. It's called an identity matrix. So here it is. Here are some examples of the identity matrix. If we use capital letter I to represent identity matrix, and if it's a 2 by 2, well, we just write a number 2 on the bottom. It's a 3 by 3, write a 3. 4 by 4, write a 4. As for how identity matrix is set up, the diagonals are going to be 1s. 1s and 1s. Everything else are just going to be 0. And it has to be that diagonal going from top left to bottom right. It can't be the other way. The other way would actually flip the matrix. So again, identity matrix is this. And whenever you have a matrix multiplied by an identity matrix, you are going to get the exact same matrix back. There's no reason to actually do the multiplication. Now the last part of today's lesson. Is matrix multiplication commutative? Let's find out. So commutative means, for example, addition is commutative. Like 2 plus 3 is the same as 3 plus 2. You can flip them around. You can move them around. Or multiplication is also commutative. 2 times 3 is 6, which is the same as 3 times 2. And here we are trying to find out what if you multiply two matrices. Would they be the same or not? So you can pause here and try to work with this example. There is a typo. There's no 5, 6, or 7, 8 in your notes. So these are two matrices, R and S. Find out what is R times S and what is S times R. Just a bit more practice on the multiplication. I'm going to start writing the answers. They're all 2 by 2s. So clearly our result is going to be 2 by 2 and we can actually multiply them. First row, 3, 2, 3, 2, -1, 0 for second row, and then first column, -2, 1, -2, 1, -2, 0, and then 1, -1, 1, -1. Lastly, multiply, add, multiply, add, multiply, add, multiply, add, and that will give you an answer of -6. Then 3 minus 2 is a 1, and then it's a 2, and then it's a -1. That's the first one. Second one, I'm going to have S times R here, 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 here. These are my spaces. S times R. First row in S, -2, 1, -2, 1. Second row, 0, -1, 0, -1. First column inside R, 3, -1, 3, -1. Second column, 2, 0, 2, 0. Lastly, multiply and add. Multiply, add, multiply, add, multiply, add, multiply, add. Final answer, -6 minus 1, -7, -4 in the second space, and then 1 in the third space, and lastly, a 0. As you can see, they are not the same, which means we cannot flip the matrices. In matrix operations, position play an important role. Matrix multiplication is not commutative. You can't move the matrices around. Notice that we haven't mentioned anything about division. That's because we can't actually divide matrices. But we can't find a clever way to accomplish the same thing. Let's think. We have solved the equation like this. One way, 5x 30, we can choose to divide by 5 on both sides and x equals 6. Or here's a different way. That kind of is the same thinking, but it's slightly different. We can also choose to multiply by 1/5, which is the inverse operation. We didn't do division, we actually multiplied. We still kept multiplication, but we are using the reciprocal, so we can still get x equals 6. So now for matrices, we are not going to divide, we are going to use something called inverse. We are going to do inverse matrix so that we can actually, in a way, do division using multiplication. And that is the last bit of this lesson. As you may notice, this procedure does require some practice, so please make sure you practice enough. That is everything for matrix multiplication. Thank you.